In this lesson, we're going to show you how this man, Ernest Rutherford, discovered that the positive part of the atom was concentrated in the very center in an unimaginably small space. And he also discovered that the positive part of the atom was made up of particles that he called protons. Most chemistry textbooks explain that the nucleus of the atom was discovered by Rutherford by using what they call the gold foil experiment, in which he bombarded a thin piece of gold foil with alpha particles. And while most textbooks do make reference to the gold foil experiment, very few of them explain exactly where alpha particles come from, or how Rutherford discovered them, or why he would bother to bombard gold foil with streams of these particles. A good place to start the story of the discovery of the nucleus of the atom is 1895, because that's the year that Rutherford received a scholarship from New Zealand to do research in any university in the world that would accept him. And Rutherford chose the Cavendish Lab at Cambridge University in England, where J.J. Thomson was doing his work that led to the discovery of the electron. It didn't take long for J.J. Thomson to realize that Rutherford was an extraordinary researcher, so he took him under his wing and gave him a laboratory to work in. In the same year that Rutherford was setting up his research, two very important discoveries were made which attracted Rutherford's attention and directed his research. The first was a discovery by a man named Wilhelm Röntgen that very strange radiation seemed to emanate from cathode ray tubes that were put under very high voltages. He noticed that a screen that was covered with fluorescent material near a cathode ray tube that he was investigating started to glow when he turned the cathode ray tube on. When he covered the cathode ray tube with black paper, he was very surprised to see it had no effect on the glowing fluorescent material. But when he placed thick sheets of metal between the cathode ray tube and the fluorescent screen, the glowing stopped. So he knew that the radiation was absorbed by certain metals. He called this unknown radiation X-rays, X for unknown. Also in that year, a man named Henry Becquerel discovered that uranium ore released these same rays that were discovered by Röntgen. Furthermore, he discovered that there were at least two other forms of radiation different from X-rays that seemed to radiate from uranium ore. But he was distracted by other research and didn't put a lot of time into investigating these radiations. It was Rutherford who did the research to discover the nature of these new radiations that were coming from uranium. In 1898, during his last year at Cambridge, Rutherford set out to determine how well certain materials absorbed the radiation produced by uranium. The setup Rutherford used to conduct this experiment consisted of two metal plates, as shown in the diagram here. The bottom plate was coated with a thin layer of uranium, and the top plate was designed so that when the radiation from the uranium struck the top plate, it produced electrical current, and the electrical current was directly proportional to the amount of radiation hitting it. He then placed successive layers of very thin aluminum foil over the uranium. When the first sheet of aluminum was added, Rutherford found that it diminished the radiation coming from the uranium by about 50%. And the same thing happened with the second and third sheets. Each one of those sheets absorbed about 50% of the radiation falling on it. But when he added the fourth sheet, he found that the radiation was only diminished by about 20%, and that continued for up to 12 sheets. This was an important discovery because not only did it confirm Becquerel's finding that there was more than one type of radiation coming from uranium, it also showed that one of the types of radiation was very easily absorbed by just a few thin layers of aluminum. Shortly after making this discovery, Rutherford was offered a position at McGill University in Montreal, Canada, where he continued his research on uranium and also on radium, which was a new element discovered by Madame Curie. At McGill, Rutherford set up an experiment which he could create a beam of radiation coming from uranium. He did it by putting the sample of uranium in a lead box with a hole in it. The lead absorbed the radiation in all directions except that through the hole. When negative and positive plates were placed on either side of the beam exiting the hole, Rutherford was amazed to find that it was comprised of at least three different types of radiation. One type was positive because it got attracted to the negative plate. Another type was negative because it got attracted to the positive plate. And a third type was not affected at all by the charged plates. Rutherford named these radiation types alpha, beta, and gamma. The negative beta beam, shown in red here, turned out to actually be electrons, the same electrons that J.J. Thomson discovered. The alpha beam, shown in green here, the positive beam, actually turned out to be made of particles that were almost 8,000 times heavier than the electron. This was calculated by measuring the amount of deflection of the alpha beam compared to the beta beam. The alpha beam deflected very little compared to the electron beam. The gamma beam turned out to be not made of particles, but rather were comprised of electromagnetic waves, which we'll talk about later. It turned out that it was the alpha beam that was being stopped by just the 3 sheets of very thin aluminum. Alpha beams had almost no penetrating ability. In fact, it was discovered later that even thick paper could completely stop alpha particles if the paper was thick enough. And as shown in this diagram, beta particles can also be completely stopped by aluminum if the aluminum is thick enough. But the gamma rays go right through aluminum and can only be stopped by heavy metals such as lead. In 1908, Rutherford took a position as professor at the University of Manchester in England, and it was here that he did his experiments that led to the discovery of the nucleus. Rutherford had already determined that when a beam of alpha particles passed through thin sheets of metal foil, that the alpha beam actually spread out a bit or was diffused as it exited the metal. And he wanted to figure out if there was a connection between the thickness of the metal and the amount of diffusion. So in Manchester, he assigned 2 of his lab research assistants, Ernest Marsden and Hans Geiger, who invented the Geiger counter, to investigate this phenomenon of diffusion. They decided to use gold foil because it was so soft it could be rolled into extremely thin sheets, and they could make very slight changes in the thickness because of the ease of working with the gold. Here's a picture of the equipment that Marsden and Geiger used to detect the alpha particles. Here we see a piece of gold foil placed in the center of the apparatus with the source of alpha particles directly behind it. Rutherford used radioactive radium as a source of alpha particles. On the other side of the gold foil, we can see a microscope which has a scintillation screen attached to the end nearest the gold foil. A scintillation screen is a screen that glows or lights up every time even one alpha particle strikes it, so that by looking through the microscope, you could detect any time an alpha particle struck the scintillation screen. The cylinder to which the microscope was attached to could rotate 360 degrees around the gold foil, making it easy to measure the angle at which the alpha particle struck the screen. As expected, the alpha particle struck the scintillation screen and showed very little diffusion or spreading out. But as the microscope was rotated past the main beam, they were shocked to find that every once in a while a slight scintillation was noticed many degrees away from the main bright spot. When these results were brought to Rutherford's attention, he directed the researchers to go back into the lab and make very accurate measurements of the angles and the frequencies at which the alpha particles were scattered. And after many months of data collection and years of mathematical analysis of the results, it was concluded that the only way that the alpha particles could be scattered at such great angles, even bouncing backwards on occasion, was if all of the positive part of the atom was concentrated in a very tiny space at the center of the atom. This new model explained why most of the positive alpha particles went right straight through the gold foil, because most of the atom was empty space. And when a positive alpha particle got near the positive nucleus of the atom, then it would deflect, since like charges repel. And if an alpha particle happened to hit the nucleus directly, the nucleus being the positive center, if an alpha particle hit it directly, it would bounce backwards, which is why when the microscope was turned behind the gold foil, occasionally they would see that an alpha particle actually went backwards. This made Thomson's plum pudding model obsolete and replaced it with a new model in which all of the positive part of the atom was located in a very tiny center we now call the nucleus of the atom.